So the basic concept that we're going to be covering over the next 12 weeks is to ask a relatively simple question, which is, do two observers, right? So observers in the physics sense is basically experimentalists or well, really anyone who's able to do a measurement. Do two observers agree on the same laws of physics, right? So if they're looking at the same doing the same experiment in two different locations, or looking at the same experiment but from two slightly different perspectives, do they agree on the same fundamental laws of physics? So I ask examples here, like what we'll do an awful lot in this course is talk about people on trains. So do the laws of physics to someone who's sitting on a train that's traveling at a particular velocity, do they agree on the sort of laws of physics that are controlling everything around them compared to someone who's standing stationary or someone who's accelerating or any other situation? So for this, the answer, so I'd say the answer must be yes. For physics to be universal. And this notion of universality is critical, right? Because that's really what physics gets at. We're not interested in specific examples or specific laws that are, let's say, things that happen in very controlled circumstances necessarily. We want to be able to talk in generality. We want to be able to say, well, here is a governing law that explains everything. That's why Newton's laws of gravitation were so remarkable. It explained everything as, you know, like innocent as things dropping to the floor, but also explained why planets stayed in orbit, right? It had applicability across vastly different scales. That's the kind of notion of universality that physics always strives for. So if we think about this notion of relativity and the relativity of the laws of physics, this concept goes way back. So in fact, if we go back to Galileo, sort of circa 1600s or so, he formulated a notion of relativity. He said that no mechanical experiment can determine if you are at rest or in motion at a constant velocity. So what he's saying here is that there is no way for us to be able to tell the difference between if we're moving at a constant velocity or if we're sitting still, that they are essentially, as far as an observer is concerned, fully equivalent. He's essentially saying here that the laws of physics that you would observe will be identical to those two people. The thing is, relativity does imply, like the fact that here we have one observer is moving and one is stationary, we know they are experiencing, or they should see slightly different things, but the laws of physics somehow are the same. So what we want to establish is what we call the notion of Galilean transformations. We want to define how were sort of events and these, let's say, like this sort of constant velocity motion, how is it defined in this Galilean term? And then that's what we're going to see breaks down. We're going to see, thanks to Einstein's ideas, that this breaks down. But let's, just as a very quick introduction, what did Einstein come along and say? Because he built on essentially this similar concept. So in 1905, so Einstein changed our physical understanding of relativity. By proposing to, I would say, simple with a question mark, postulates. Right? Postulates are just assumed truths, right? In mathematics, we call them axioms. In physics, we often say postulates. Same like concept. Postulate one, he said that all inertial observers deduce the same laws of physics. That is just a restatement of what Galileo had already said. Right. So we will define what we mean by this concept of inertial in a couple of minutes, but it's essentially a body or a person or an observer that's moving at a constant velocity. So he basically was just restating Galileo, but introduced another postulate, and that's the one that I've already briefly mentioned, that the speed of light in vacuum, okay, so there's a few little caveats on this statement, is the same in all inertial frames reference and is independent of the motion of the source. So the important parts here is that speed of light is the same in all these inertial frames, so we'll define what we mean by those things, and that it is independent of the motion of the source. And this independence is really where the break from the Galilean ideas come from. And the reason that he postulated this was for good. I mean, there was a good motivation. Experiments at the time had been trying to understand the speed of light. We'll talk about it in the next lecture. There were experiments being done trying to measure what is it that light is moving through. What had been discovered in the 1900s was that light was a wave. And we all know, if you look at how does a wave propagate, it has to have some medium to travel through it. Like water waves have to travel on a body of water. Sound waves have to travel through the particles in air. By the same token, light then had to travel through something. They proposed a notion called the ether, the luminiferous ether. And then what they wanted to study was understand, well, what is the speed of the ether? Because the light had to travel through something. What he proposed, though, like the experiments demonstrated that wasn't the case, that the speed of light was just constant no matter where they looked. And so he came up with this idea, and by defining, just saying, well, speed of light appears to be an absolute truth. It's just a fundamental limit that no matter what experiment I do, I always get the same answer. The only way I can reconcile this is I have to change my other basic understandings. So that's what we're going to see over the next little while. So what he said, and what had been derived already, was that the speed of light, what we'll start defining it as, is just this, using this little symbol c, is 299,792,458 meters per second. I will never write that number out again. What we approximated to is 3 by 10 to the 8 meters per second. And that was something that we already knew. It's not Einstein didn't come up with this. This comes directly from Maxwell's equations, right? So what you will learn whenever you do your electromagnetic theory in a couple of years' time are Maxwell's equations, how we understood electromagnetic radiation. And from Maxwell's equations, this number does drop out. So people at the time knew that light traveled at this speed. They just couldn't really motivate exactly why. And what Einstein came along and basically said, you cannot ask the question why. Light does what it does. It's a fundamental limit that the universe has just given us. This is a kind of God-given truth as it was. And so, but if you accept this, and that's what Einstein does, he accepts this as a truth that that's it. Speed of light is fixed as this number, and then looks at what the ramifications of this are. And then what has happened is we've tested those theories, and it has been proven to hold true. So if we look at what the consequences of this are, just as a very sort of first glance. The consequences is that this c, the speed of light, is the ultimate speed limit for any object, particle, signal, anything you want. That nothing can go faster than this speed. This is the absolute upper speed limit for everything in the universe. The knock-on, though, also from this is that, well, since c, which is the, just from our basic mechanics, distance traveled by light divided by the time taken, and is equal to constant, which is, we say, 3 by 10 to the 8 always. If that is always true, if you always observe the same thing, no matter how far that light apparently has traveled or how long it has taken, right? So different observers can be moving in, let's say, in these different frames, doing different experiments, and they always get the same number. The only way for that to hold true is if this ratio is somehow always fixed. And the only way I can fix a ratio, for instance, if I change the time or change the distance, let's say, light's travel, then the only way that I can come out with the same number is by also compensating by that change with the other number. Essentially, that fact that these things are constant then implies that we need to change our understanding of space, time, energy, and mass. It's the only way for that to be true, right? And we'll actually see the easiest things that we're going to see that it fundamentally changes is our very notions of distances and time, right? It impacts exactly what it means for time to pass or for distances to have any particular meaning. So it changes these, like the very fabric of what we see. So, any questions so far? Okay. So before we really launch into what Einstein gave us, let us quickly recap in case you've forgotten or you haven't covered it yet, just a little bit on what the state of the art was at the time, what classical mechanics and Galilean relativity essentially defines. So what Galileo's concept of relativity formalizes Newton's first law, or vice versa. And in fact, that's what Einstein's first postulate says, that the first law is saying that an object remains at mass or a constant velocity unless acted on by a force. Right? So then this is essentially what we're going to use. We use Newton's laws to essentially define what we mean by this concept of an inertial reference frame. So we're going to see why what that is in a second. But there's this concept of a force. And so that's where Newton's second law comes in. So we're not really going to be dealing too much with this, but just for completeness, what Newton's second law told us was that the force was proportional to the mass of whatever it is that was moving multiplied by some acceleration. And that's necessarily dependent on the observer. If you have, it becomes more dependent on the observer, on the motion in particular, right? The forces that are experienced are dependent on how a body is accelerating, which means how its velocity is changing. So what we'll find is that this allows us to define the concept of an inertial frame by basically saying it's something where Newton's first law is upheld, and by a corollary of that statement means that there are no forces acting on it, right? So which means that the F in this instance is going to be 0. So let us define now a frame of reference. So you'll hear me saying this a lot. This refers to an observer's state of motion. So as examples, experimentalists in the lab, say, here are some trains. Okay. Frame of reference is just a way of saying essentially the circumstances that the observer is in, right? So it's going to define the state of motion. That allows us to then add this additional caveat that an inertial frame of reference is one which Newton's first law holds, i.e., a body at constant velocity. So, for example, passengers on an accelerating train. Do we think they are in an inertial frame of reference? I'm just throwing out there to see whether or not anyone will actually answer on the second day of class. No, they're not, right? So the reason that they're not in an inertial frame of reference is because Newton's second law is in play. There are forces acting. What we said is Newton's first law is that they will remain at rest or at constant velocity unless acted on by a force. So, and a force implies an acceleration. So what this is saying is that if passengers on an accelerating train are not in an inertial reference frame, that's because things are accelerating, right? They themselves are accelerating, or by the same token, to them, the things will appear to be accelerating away from them. It's actually very difficult to get a proper inertial reference frame. In fact, everything that we're going to talk about, we're going to use kind of the best approximation to assuming things are inertial frames. That's what good theorists do. And in fact, most of the time we'll be talking an awful lot about observers on Earth. Whether Earth is an inertial reference frame, intuitively, your initial reaction based on what I just said should be no. And that would be technically correct, because we say Earth is approximately an inertial reference frame. Since orbital velocity is about 30,000 kilometers per second, and it is rotating. Right? So the Earth is moving, but it's not moving in a straight line. It's actually orbiting around things, right? And then if you've done any kind of, if you understand, or if you've studied any, let's say any physics, you know that velocity is a vector component, right? It's not just the magnitude, it's not just how fast something's going, it's also the direction it's going. If that direction is changing, it implies there is an acceleration. There's an angular acceleration. The Earth is also rotating, so it also has an additional angular rotation. The reason that it's a good enough approximation to say it's an inertial frame is because those numbers, although 30,000 kilometers per second sounds big, is actually tiny in comparison to what the speed of light is. So it is sufficiently close to a body at rest that we can pretend like it's an inertial reference frame. And this works to an incredibly good approximation. So we are going to treat the Earth and everything in it as essentially a well-defined inertial frame, accepting the fact that it's not quite exactly right, but it's close enough. And the reason that we can do this is because of the sheer enormity of the speed of light. Speed of light dwarfs this number. And in fact, it dwarfs even more the rotation of the Earth. The Earth rotates at something like, I think it's something like 100 kilometers per second or something like that, which is, again, orders of magnitude smaller than how fast it's moving through the solar system. But these numbers are so small that essentially we can treat it as an inertial frame of reference. And so the important thing to take from here is that all inertial frames are equivalent with respect to the laws of motion. That's essentially, again, just stating Galileo's concept of relativity, that essentially the laws of physics in any given inertial frames will deduce the same laws of physics, or will be governed by the same laws of physics. So to make this maybe a little bit more tangible, I think what's very often kind of presented is this kind of basic picture, and probably how Galileo maybe came up with this concept was that if you're sitting on a ship, and if let's say it's a very calm sea, so there's nothing going on, and it's just moving at a constant velocity, you can let's say, translate this exactly to the examples of trains that are moving at constant velocities, you can do all of the normal things and you wouldn't notice the fact that you're moving. So as an example here is you can play tennis, right? Is the kind of example that if you're on a ship that's moving essentially at a constant velocity, you don't notice that it's moving. And then you can bat balls back and forth and it will appear as if exactly the same as if you were doing it standing on the earth, apparently stationary, right? This is the kind of concept of Galilean. This is the sort of core idea of Galilean relativity. The fact that even if you're moving, as long as you're moving at constant velocity, then you will basically, all of the motion that you would experience would be exactly the same as if you were standing still. Are we happy enough with the notion of Galilean relativity at this point? So we're going to formalize it now in a second. Cool. Okay. So we want to find a way, like what we're going to need throughout this course is a way to kind of formalize a few of these ideas and how to represent these concepts a little bit more mathematically. So we ask a question of how do we represent an inertial frame? So as I say, we're going to see an awful lot of examples of this sort of thing. People on trains and people standing on platforms. It's kind of playground of relativity often. So in this diagram, what we have is essentially two observers. And so there are two frames of reference here, right? What we said is what defines an inertial reference frame is that the frame of reference is moving essentially at a constant velocity. That velocity can be zero, so it can be stationary, or it can be moving at some fixed but must be constant velocity. And so the example of a person standing on a platform and a train moving past at a constant velocity is a good demonstration of two different reference frames, right? So the train is moving at a velocity in one direction, and we have two observers standing here. So as I said, there are two inertial frames. So what I call observer A on the platform. And we would define this inertial frame. I'm going to call it S, and I can define, let's say, the coordinates, right? Like, so we're going to start talking about where things happen and when things happen. So in order to define where something happens, we have to give it coordinates. How we work, how do we give coordinates? Well, we give the spatial coordinates, right? We can do it using whatever coordinate system we want, but we will work with Cartesian coordinates, right? So X, Y, Z coordinates is enough, right? So he will define everything to happen in his inertial frame based on these X, Y, Z coordinates. Observer B on the moving train is also in an inertial frame. We're going to call this S prime. And again, it will have similar coordinates, X prime, Y prime, Z prime. Which you choose to call S and S prime is completely arbitrary. And that's the kind of essence of relativity, right? There is no kind of absolute notion of motion here. We can say like the two reference frames appear are basically equivalent. To the observer on the train, they are essentially stationary. They're not moving. They're on the train. The train is, we know, is moving, but to them it appears as if the platform is moving away from them, and that's a perfectly equivalent view. So you can define your what you call kind of rest frame or moving frame essentially interchangeably. But we can sketch these out a little bit clearer, right? So let's look at what their axes actually look like. So if I think about what my observer A's reference frame is, so they have their X, Y, and Z coordinates, and then there's some origin where they're essentially standing, and they define where everything is relative to them, right? So that's how they define where any object or any event might be happening. The observer B on the train has a similar set of axes, x prime, y prime, z prime, and this thing is moving. The difference is that this is moving at some velocity v. And so the way this is how we normally will sort of think about events happening for the two different observers, right? So I have my reference frame for observer A is S, and my reference frame for observer B is S prime. So this is what we see from here is that the standard setup is to fix y equal to y prime and z equal to z prime, right? That's what we see, right? If the observer who's on the platform observes something happening at some y coordinate, according to the moving axis, it'll have the same value of the y coordinate. The only thing that's actually changing here is the x direction, right? And that's because we fix x and x prime to be parallel to the relative velocity. Right. Then this just allows us to simplify things greatly. It means that we only really need to worry about relativity in kind of one direction, right? And like an object is always moving in some direction, right? So if it's going, you just orientate. What we always do is we orientate our axes, right? So for where we're defining where anything happens, so that the x direction is always parallel to that velocity, and we can always do that, right? And so then this allows us to kind of cleanly define things, and it's going to allow us to define in a proper way what we mean by an event. The last thing that we do is we set time t equal to t prime equal to 0 at some agreed point. For example, when O equals O prime. This is a little subtle. Oh, that was O prime. So we're going to need this later on, because in order to talk about relativity, right, we're going to see that we also need to bring time into the notion, and that's going to mean that we need to define a notion of simultaneity, right? When things like the actual when something happens and when two things happen at the same time, and for that we need to make sure that everyone agreed on it at some prefixed time before motion all started. So that's what we're doing here. What we say is that in addition to fixing the direction of the velocity being essentially parallel to this x-axis, we also assume that at some point the origins coincided. Again, it's not a hugely restrictive physical assumption. We're just assuming that before we started doing any experiment, the two reference frames had some common origin, and then one was moving off in some constant velocity. And you can always do this, right? So what we'll see in the couple of lectures time is how do we define synchronization? How do we line up essentially two clocks? That's one of the core things, but you can always do it. But why we need this and why I've introduced this this structure is that it allows us to properly define an event. So an event occurs at coordinates x, y, z, t in S, and x prime, y prime, z prime, t prime in S prime. And already you kind of see that we're slightly extending what you're maybe used to thinking about when we talk about where something happens. We've introduced an additional, looking at these kind of vectors, like a three-dimensional vector is probably not that uncommon to you. So defining where something happens needs those three coordinates. We've added an additional coordinate here, which is time to define when something happens. This is essentially what space-time is, right? It's nothing that particularly fancy. It's just extending this representation. Now, what's critical is that Newton and Galileo believed in an absolute notion of time. All right, so that time, like when something happened, did not matter, was not impacted in any way by relative motions. So they believe that, like essentially that while things could be moving around, and so you could define where something happens relative to you. I mean, as an example, like if something drops here, I would say it happens in front of, let's say in front of B. But to you, it's happening it's happening at essentially a similar position. Okay, sorry, scratch that. Easier way to sort of get an intuitive. If I'm here and you're standing there and something drops here, I say it happens on my left, you say it happens on your right? So there's a kind of slight notion of relativity there. But we would both agree on when it happened, right? And that's kind of the essence of what Newton and Galileo were saying, was that there was an absolute notion of time. There was a kind of universal clock that everything in the universe happened at this, essentially at a fixed time, that this was just woven into the fundamental fabric of things. And then with that notion, with that idea, we can relate events into reference frames. The last couple of minutes. So what we're going to finish with now is just to see, well, what was it that Galileo was thinking about? This. So what we've just said is we can define something like some point, and we call this an event. It has an x, y, z coordinate. It has also an x prime, y prime, z prime coordinate. So an event that happens at some time t. We have a look at what happened now. Imagine what we've assumed is that these two axes were simultaneous at t equals 0, right? So that was our synchronicity, right? We've assumed that the two observers were at the same point, and then things started moving apart away from each other. So one stays fixed, the other one's moving at this constant velocity. So, and then something happens at time t. Where is the second axis, the moving axis after that amount of time? We use our basic, like, speed is distance times time. And so we can see that the axes have moved relative to each other, a distance v times t, right? That's all that's happened. If the moving observer is moving at a velocity v, the distance it covers in a time t is v times t. So that's how far those axes, essentially their relative axes, have moved apart from each other. We can therefore then very easily define where this event is in relation to the to these two inertial reference frames. So this gives us the Galilean transformation. That x prime, if we have a look at it here, the event happens at point x according to the reference frame S. What is the relationship between that point in the reference frame x prime? Well, the axis has moved a distance vt, so it's happening at this point, which is going to be, x prime is then going to be x minus v times t, right? Because the axis has moved. It's essentially discounted this portion along the x-axis, and so we take that away in order to find what the corresponding coordinate is in the x prime axis, right? So if you just look at this diagram, you can see that relationship. Based on what we assumed earlier, though, our y prime and our y prime and z prime coordinates aren't changed. Right? So it happens at the same y coordinate and the same z coordinate, and importantly, the same t prime coordinate. And this is what defines the Galilean transformation. Essentially, just it allows us to relate where something happens, working on the assumption that there is this notion of an absolute time, that the when it happens hasn't changed. This, so the classical, and what I'd say is non-relativistic addition of velocities follows. For example, trolley moves on the train with velocity u prime relative to the train's velocity of v. Then what do we have? X prime. No, where is it essentially? So it's going to be u prime times t prime. So the event. So this would be in my train frame. Using this Galilean transformation, then means in the other frame, x is then equal to u prime t prime plus vt, because the axes are moving, which using these relationships, we can then factorize out u prime plus v times t. Then implies for the, let's say to an observer standing on the platform, they would see that they would assume that the trolley is moving at a velocity of u prime plus v prime. So if you're on the train, you only see the trolley moving at a velocity of u prime, while an observer who also sees the train moving will see that it's moving with the addition of the velocities, that the two velocities are added together. What follows, and you can kind of show it yourself a little bit, is that if it accelerates, you'll also get Newton's second law coming from here as well. Right? It'll also follow. If the fact that the train, as long as the train is moving at a constant velocity, then both observers would still deduce the same Newton's second law, because even if the trolley were accelerating, so it's on the train's moving at a constant velocity, and the trolley starts accelerating, both observers, someone who's standing on let's say on a platform, observing the whole thing moving, or someone sitting on the train, they will still see the trolley experience the same force, because the only velocity that's changing would be the trolley velocity itself. So when you use the fact that acceleration is the derivative of the velocity, you'll see that Newton's second law drops out. The two perfectly agree. I'll write it into the notes later on. Kind of don't want to overload you now, and we're almost out of time. So let me pause there for a second. Are there any questions at the minute? Main takeaway from today is just we've kind of formalized a little bit the notion of a Galilean transformation, or just essentially all we've done is defined where does something happen. This whole 1 hour lecture has just been basically building up to, I need 3 coordinates in space and 1 coordinate in time. And traditional common sense notions say that the time, let's say when something happens, is essentially always the same. What we're going to find is that Einstein's second postulate, the fact that the speed of light is this absolute upper speed limit, breaks that. Essentially, we'll find that this Galilean transformation holds beautifully for small velocities, but once you start getting up to speeds that are appreciable amounts of fractions of the speed of light, something fundamentally has to change. And we're going to in Thursday's lecture, we'll cover a little bit of the experimental evidence for why that was needed before we eventually get to what we call the Lorentz transformations. So I will stop there.